What is ServoTuner? ServoTuner is a graphical tuning aid that assists the user in tuning the Compumotor's 6250's position loop and the drive system. When using the drive in velocity mode, it is necessary to tune the drive first, using Drive Tuner, and then tune the 6250. When using the drive in torque mode, only the 6250 needs to be tuned. ServoTuner example. Our equipment today will be a 6250 servo controller, two OEM 670T drives, an OEM 2300 motor for axis 1, an OEM 2303 motor for axis 2, Motion Architect and ServoTuner software.
We will now demonstrate the use of the 6250 Servo Tuner. As you can see, the motors are not tuned for optimum performance. The 6250 Servo Tuner in Motion Architect facilitates the tuning process.
We will begin in the main menu of Motion Architect. The product must first be selected. The default is the 6200 and the 6250 servo control must be chosen. That changes our main menu in Motion Architect. 6250, the 6250 tuner must be selected under the Utilities menu. This is our main screen. We will start with the top menu. Before beginning, we must be connected with the 6250. That is under the Communications menu. Next, we must be set up. First, we will set up the system. The participating axes will set the active axes, either axis 1 or both axes. The trajectory servo ratio changes the ratio between the servo sampling frequency and the move trajectory update rate. Next, we will set up the encoder. The setup parameters will set the encoder resolution and the maximum allowable position error before a fault occurs. For our system, axis 1 will be set at 2000, and axis 2 will remain at the default value of 4000. The next thing on the menu is Tune. This is an automatic gain selection. A customer can use this feature to have the Servo Tuner calculate theoretical gain values based on the motor load data. These values give a great starting point, but are typically tuned way too tightly, and the gains often need to be reduced to satisfy the application. Next, we will ensure communications. Under the View menu, under COM Display, we will type T gain. This response tells us what our tuning parameters are currently set to. We will now proceed to our Motion, Capture, and Graph menus. We will go with the Step Profile. This move type typically gives the best representation of the system's overall characteristics. A step move commands a set distance with an infinite acceleration. This type of move will usually excite all of the system's characteristics so we can see its overall responsiveness. This can usually be used to do with the majority of the system's tuning. Recommended small step distances to avoid saturating the analog output, which could disguise the actual system's response. The Trapezoidal Profile. This can be used to stimulate the application's typical move profiles to see how well the system is performing. This can also be used for the overall system tuning. And the S-curve profile is identical to the trapezoidal profile, except X-curve accelerations are used. The capture menu has data to be captured. This will specify what data you want the ServoTuner to capture during the subsequent moves. You can specify as many fields as desired, but more items will decrease the number of samples of each individual item. The data sampling parameters sets up the sampling information for the 6250 tuner data acquisition. The trigger point that initiates data capture will specify what event will initiate the data capture. And the data sampling interval is used in conjunction with the trigger point. This feature only applies to the trapezoidal or S-curve profiles. The first under graph, graph 1 is the red plot while graph 2 is the blue plot. The graph setup can show you up to 2 different graphs on the same plot. Make sure you have captured the appropriate data with the Data Capture Setup window, or your plot may not show up since no data was gathered for it. It is important to make sure you switch the axes on both axes and both graphs when going between axis 1 and axis 2. There is no universal axis select button. The graphs can be scaled, but the default values are usually the most useful. Some useful tuning graphs are actual position and commanded position, both versus time, actual velocity and commanded velocity, both versus time, velocity error versus time, and analog servo output versus time. We have chosen commanded position versus time for graph 1 and actual position versus time for graph 2. We are now ready to start the tuning process. We will start with the default values of SGP at 0.5, notice our response. The top line is the commanded position, while the bottom line is the actual position. Our goal is to have the two lines in sync. Does not reach the commanded position. We must increase the proportional gain until it does. We will first increase it to 5 and then start tuning again. As you can see, the actual position overshoots the commanded position, and there are also oscillations. On page 36 of the 6250 Servo Controller User Guide, there is a flowchart designed to step the user through increasing and decreasing gains to achieve optimal response.
As seen in the graph display is an oscillating underdamped case. In our flowchart, that puts us right here. Our flowchart tells us to increase the velocity gain until we achieve one of these graph profiles. The velocity gain increase dampens out oscillations. Advice from our flowchart. We will now increase the velocity gain from 0 to 5 and start the tuning procedure again. This seemed to have decreased our oscillation, and we have a critically damped case, which is what we want for optimal servo tuning. Parameter response achieved through ServoTuner. We will contrast a tuned axis with an untuned axis. What affects our tuning head on axis 1? Notice the stiffer response of the system. Compare that to the behavior of the untuned axis. Notice the ringing.
ing, 'due to poor tuning.
'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'Due to poor tuning. 'D
now concluded tuning for axis 1. In order to tune axis 2, we must first switch our tuning gains to axis 2. Then we must go into Data Acquisition, Motion, and enable Motion for axis 2. Under Capture, let's first change the data to be captured to axis 2, and then add our commanded position and actual position. And then change our trigger point to axis 2. Finally, under Graph 1, we must change to axis 2. In Graph 2, we must also change to axis 2. We are now ready to start tuning on axis 2. The same procedure is used for optimizing our tuning parameters on axis 2.